Take two.
From this job's video today.
Good?
We're
Okay.
filming.
So yesterday, what did we do? We did,
Ideal gas.
Pivner.
good job. Can you say that one more time?
Pivner.
There we go. So what is Pivner? What gas law is it for?
The ideal gas law.
The ideal.
Like overall.
Okay. So when we did the calculations yesterday, can y'all get that worksheet out just for a moment? As y'all are getting out, do y'all have any questions with the calculations that we did yesterday? Just that part, not the lab part.
Did y'all have any questions or anything on that? No? Okay.
Okay, good. So we're gonna move on to the lab activity. Okay, so I know a lot happened, so we're just gonna kind of go over the observations that we went over. So when we did the lab activity, do you think the size of the bag would affect the lab at all? Like, what if it wasn't 0.94 liters? What if it was smaller? Do you think the expansion of the bag would?
I think if the bag was smaller, it could have maybe popped or something,
Okay.
or it would have, like, yeah, I think if we put the same amount of baking soda and vinegar in there and made the bag smaller, it would pop because it wasn't like, it inflated, but it wasn't like necessarily like firm
Mhm.
or whatever. You could still like squeeze it a little bit, but I feel like if it was like maybe a smaller bag, it would definitely explode.
Yeah, it would either like pop or just like take up more space.
So what if we use the same amount of volume bag, 0.94 liters, but we use more baking soda? We still have 46 milliliters of vinegar, right? 46?
It's the same thing as if you're using a smaller bag. It would just be like more, there would just be more pressure in the bag for it about to pop.
Wait, do we know which one's the limiting reactant?
Um,
Or should we-
Well, that's a good
Yeah.
question.
That's what we were going
Go
for.
back.
If you have more baking soda than your vinegar, then which one is your limiting reactant?
The
vinegar.
The vinegar, right. Perfect.
What did you guys calculate yesterday on how much each one needed? What was, when you did the PV equals NRT, what did you find? What letter did you solve for?
Oh, the moles.
The moles, right?
Correct.
So, and it was all 1 to 1 to 1 to 1 in the balanced equation. So you had equal moles, and then you went and calculated how many grams of each one, right?
Right.
So that was the exact amount of each one to be perfect, so neither one was the limiting reactant. So then how could you adjust that to get, find out, okay? That's how you find out the limiting reactant, you had the exact number of grams of each one that you needed for perfect. So if you had more baking soda than what you calculated, then the other one, the vinegar is limiting reactant. If you added more vinegar, it's about 46 or whatever it was supposed to be, you put 50, well then the baking soda was your limiting reactant. Okay? Now, we never did the math calculations for limiting reactant, but we did it by definition, so that's a good question.
So why do you think it fizzed up in the bag?
Chemical reactions.
Yeah. Can someone go a little bit deeper? Maybe. Yeah.
The gas releasing from the liquid, like
Okay.
separating.
Yes, that's good. Okay, so let's go. Why do y'all think it was cold? I heard a lot of people saying it was cold. So why was it cold? Someone said it yesterday. It was right on the line. I think it was Hudson.
It is an endothermic reaction.
What is an endothermic reaction?
It's a reaction that causes the heat to like just drop, and it's a change in like temperature and stuff.
Is there anything else y'all learned from this lab activity? Like the gases reacting with each other, the expansion of the bag? What kind of, when we did Pivner, what was it telling y'all about the pressure and the volume? It was increasing, right? Because it was getting bigger, the gas particles in there were colliding, the pressure of it. good with that? Okay. So the reason why we're asking these questions, because y'all are about to do a Phet simulation, which it's gonna show y'all gas properties. Y'all are gonna have a little container. There's blue and red particles. We could say it's our vinegar and baking soda. So it connects to our lab. So we're about to pass out these worksheets. Can y'all get out y'all's Chromebooks? Thank you. And on the worksheet, we have a link to the Phet simulation, and you will just be doing the gas intro or gas ideal.
Oh, is it
And I do apologize for the chart being small, so it is front and back, so you can write on the back of y'all's chart. And then there's additional questions on the bottom. I'm gonna borrow yours right here. Wait, yours is blue. See, it'll say the link go to, so it's all right there. Did you not have it open? Oh, it's on the back.
Yeah,
It's front and back. I was thinking it's 2 pages for some reason. I don't know why.
Alright, does anybody got a piece of paper?
Thumbs up when y'all get to the website and y'all are good with the simulation. When y'all on it. Yes, it is.
Is it load? Is it load for you guys?
It takes a while, but it loads.
See, they're not gonna just be able to play around with it.
And then, do we do the ideal one?
Ideal.
Okay. I mean, good, right, there's 4.
Oh, no.
So I had to make sure.
You're good.
Oh, here it goes, here it goes.
Yes.
Finally.
Appreciate the small things.
It's not 8. Actually, I'm wearing shorts and a t-shirt. It's probably 8 degrees.
Obviously, it's not actually 8 degrees, very humid.
Oh, it's just 8 degrees with the feet shoulders.
Yeah, you'd have like 2
It reminds me of Desmos.
That's how I figured it
Oh, dude, I hated Desmos.
No, not Desmos.
Oh, no.
Gizmos.
Gizmos.
I hated all of the
I still have that favorite or bookmark. Let me go to Gizmos. I'm gonna go to Gizmos.
No, you're perfectly fine.
I
Where's Gizmos?
don't keep any of them.
Do we not have Gizmos?
Good.
I don't have a Chromebook, so.
I don't have Gizmos bookmark. Is on utility? Oh, we moved.
Forgotten.
Check TV.
Yes, it would be ideal.
I think we're gonna change that
What was
picture size. Ooh.
Yeah.
is a calculator.
Ooh.
Oh, are we going on? Wait, what are we doing?
I'm just
Oh,
messing
what?
around at the moment.
As of right now, let's just let everyone get on this.
Oh, okay.
At the moment, the bubble.
So thumbs up if you're on the Phet simulation page and you are on the ideal simulation. You have a container in front of y'all and you have a little pump where you can pump gas particles, constant and everything. You're good?
That's so fun.
Okay. So there's an example right here for the chart. So first y'all are gonna do the chart. So you remember how we talked about the pressure and the volume increasing in our lab activity? So right here in the container, there's an example right here, which y'all can do it for yourself too. So at first it goes volume increases, temperature increases. And then it'll say pressure always or sometimes. So, and then for that, it said sometimes the pressure increases and sometimes the pressure decreases when the volume and temperature is. And then here's his explanation. So you're gonna try to explain for the reason why this is happening. Hudson, would you like to read the explanation words for me?
Yes.
Mhm.
It depends on if the volume increase is greater than the temperature increase. volume increases slightly and the temperature increases greatly, then the pressure of the gas will be larger. This is because there are more collisions of gas particles, causing greater pressure.
So is everyone good? So you're just gonna, so it already has it filled out for you, so the second row has increase and decrease. But you're gonna figure out if the pressure always or sometimes, and then you're gonna write down what you observed, and then you're gonna explain it in your own words, explanation. Okay, y'all ready? And y'all can talk, like this right here, this is group 1. Y'all can talk to each other. Group 2, group 3, group 4. Chad?
Chad.
Yeah. And group 5. That's it. No? I've been calling him Chad.
Chad.
I've been calling him Chad since yesterday. I'm so sorry. Okay. Y'all ready? Go. I'm so embarrassed. I really didn't call.
Wait. How do I increase the volume?
Look, I'm popping the lid off of this.
Do you want us to hold one of them at a time? Like you do it either way.
As of right now, don't worry about the constant, just do the chart, and then when you get down to the questions on the back, that's when it'll start asking about the constant, the size of the container, and it.
So you want us to decrease the temperature but increase the volume, right?
Okay, how do I decrease the temperature? Temperature, decrease.
How do I?
Oh,
And I make the
okay.
container smaller
First you
so
need
it
particles.
takes less
I
time.
need, oh.
We require particles.
So here's the particles. So you
Oh, here we go.
Oh, those are the particles.
Yeah.
So we have blue and red particles.
But red
Pressure's going up.
Yeah.
It's not those, you know, Michael. Okay. Oh, red particles. Now it's, oh my
Solid.
gosh.
Adding particles to it.
Yeah, you're adding particles as
And then how do you just
They're colliding, so the
That's
pressure's
so cool.
increasing.
So you're gonna have to hold it.
Look,
You lift the little bucket
look,
and down.
change,
Because it
and then
says
if you do
increase.
this,
So if
you
it's
add more, and the pressure starts increasing.
I'm trying to freeze it.
Oh,
Can you change the size?
that's so smart.
I'm trying to freeze it.
Move
the red ones
I'm gonna crack my phone.
I would not be surprised if it crashed. Be colder.
Does it matter?
Also,
how many
this
I
thing is still recording the board.
Let's see what happens when I heat it.
Somebody go do a dance in front of something.
I'm gonna pump, max it out. You know, if y'all click the particle thing, you can max it out pretty easily.
Your blue and red particles and.
Oh, I just pumped it to
No,
the maximum.
yeah, I just clicked, the maximum should be 1,000.
Yeah, the maximum is 1,000 for each.
Let's see if I can pull
Can
the top
I
off.
make it absolute zero on this thing?
Particles.
The heat's
Is it gonna
going
count?
up.
It's
Oh,
not counting me.
I exploded the top.
You made it explode?
Yes.
Yeah.
Oh, it is counting.
Okay. Make it.
No, wait, no, it's not.
Whoa. Yeah.
I didn't do that, right? I gotta decrease the volume.
Look.
How do I? Oh,
Almost a zero.
It takes forever to get that last couple of ones.
So you just add particles.
Return.
Remember, you can add blue and red particles.
Okay.
What are the red particles?
Alright, so I just decreased the
We
volume
could
and
say
I
blue
decreased
is
the temperature.
for vinegar and red
So
is
the
for baking
pressure-
soda, just to help us link with our lab activity more. Just to have a name with it.
I froze all the particles.
Can I let go?
What happened to the volume of the container?
The volume increased a lot, but when we froze them, the pressure went completely down.
Okay.
It's non-existent.
Okay.
Wait, so if I let go, does it still stay?
Yeah, it's gonna stay.
Oh yeah, let's go. Okay, so pressure always or something. So
Sometimes the pressure increases, sometimes the pressure
So we gotta heat them up.
There we go. That makes more sense.
okay, this means that it's inconsistent because volume and temperature. That's when it explodes. That's because it's inconsistent. When the volume increases, but the temperature decreases, it always stays the same because it's very stable because it's completely frozen.
Yeah.
Wait,
No,
Miss Jean, how are we supposed to decrease the volume?
With their own look.
Do we just open the lid?
Yeah, no, you pull the,
You
The handle on the left side, pull it.
You pull it.
Right.
Oh,
Yeah.
I'm in
There
there.
you
Yeah, that
go.
one, pull it. There you go.
Alright, let's go.
I could've figured out either.
Wait, did
I'm
that
gonna
increase
set
the
them at
volume?
Yes.
200.
Oh, wait.
Go,
Wait, you put more stuff in it?
Yes.
300.
Okay, ours are still frozen.
Let's do
Okay.
300.
Look, look, increase it, and then look, it's still frozen.
That's so much cooler.
Mine looks like Dippin' Dots.
It does look like Dippin' Dots.
Okay.
I serve these
Yeah,
things
do
at work.
Increases, decreases. So we increase the volume.
How would we know? Well, they're not called Dippin' Dots.
So we increase the volume and then decrease the temperature. So it's the same thing as it is before. The pressure stays the same.
So you'll just have to kind of play around with it and see, like, if, say you have like the temperature and volume, if you're increasing the temperature just a little bit, but you're increasing your volume a lot, whatever.
Oh, I still blew the top off of it when I increased the
The
volume.
pressure constantly stays the same because it is frozen. Frozen and stable.
Let's just play around with it, okay? Okay, so you increase your, increase your
I'll see the
Y'all
ice
still doing okay
man
over
was
there?
super stable. That was hilarious. Laugh at that.
Ice in the ice man.
It is funny.
Where did you pull that out of like last year's lesson?
I pulled out 8th grade Mr. Potts' lesson.
Oh my god, that was 8th grade.
8th grade Mr. Potts. He was talking about Otto the Iceman.
I remember watching a documentary on him. Actually, I may have watched it.
Oh yeah. We watched
That was virtual. You actually remember something was virtual?
It's crazy, right? I actually really liked
I
that
feel like I
documentary.
remember
It's the only
that,
thing that
but
keeps my
I
attention longer than 2 seconds.
Wait, just give them
Like
I remember
documentaries
Mr.
and
Carnes' virtual lessons because he did them in the middle of the woods. And it was amazing.
just sit in the middle of the woods.
Is the pressure?
I remember every one of those algebra
Remember
lessons.
when we?
So if it's all.
Well, if you make it interesting, then yes.
But.
Like some of the only things
I
I
still have them.
cited are.
I can pull them up on my phone. I still have those Jag TV clips because I recorded them on my phone.
We were on Jive TV, very, and we were when we were in quarantine. We were so wanted us to do it, so we like recorded like outside.
The volume increases. Wait, wrong.
Mary at Jag TV, this thing part-time at Jag TV.
My mom was like, "You should get Jag TV at Spain Park," and I'm like,
You know, when the school first opened, they had a whole studio.
"Oh
They would do the announcements live on the video on the TV. But,
Like the TVs need a little bit of
Yeah.
an update.
well,
They did a little
they
bit
would,
of
but we used to have big flat screen TVs in the hallways too.
Hmm.
But,
That's not fun.
the, announcers one morning inadvertently said some inappropriate things
Uh-oh.
when they were suddenly shocked by something, some profanity, very harsh profanity came out of their mouth. And so, as a result,
Mr. Hobbs, you're on tape.
yeah, I know. Hey,
There's too much dead air.
yeah,
That must have been amazing to watch live."
It was from
I've
there.
got it under 5. Oh.
all where the Health and Science Academy down there, that was all the TV studio.
These
Oh.
things are
We need a
slow.
TV studio again.
Under 1
That'd be awesome.
ATM.
Helmer would definitely.
Okay, y'all, hey, as you're doing this, and listen, hey, on a serious note, as you're doing this, relate it again to what you already learned with Boyle's, Charles, Gay-Lussac's combined gas law as far as direct proportion, inversely proportional. You know, as one goes up, what's happening to the other one, okay?
I got it at 0.
So don't just go through the motions.
Since the particles are frozen, they aren't hitting the container.
How did you do on that second round?
Oh, wait, watch this, Shelby. Therefore, thank you. We need to patronize you.
Now heat them
Therefore,
up again. See what happens.
the pressure is down at 0.
How's this group doing? So what are
We're
we,
doing great.
so what are we doing?
Well, I increased the volume and the amount, and decreased the temperature. It's completely frozen, and I said that the pressure constantly stays the same at 0 because the particles aren't moving and bouncing off the sides of the wall, meaning that the pressure's at 0 because that's what pressure is. It's particles
So
hitting the
would
wall.
you say that volume and temperature would have a correlating relationship?
A directly proportional relationship.
Yeah. And that would be Charles' law, wouldn't it?
Yeah. This is an example of Charles' law. Okay, so volume decreases, but the temperature increases. Okay, we're about to have fun with this. What's this showing? Uh-oh, uh-oh.
In decrease
Are you ready for this? Are you ready for this?
So you're gonna see what's happening to your pressure. So is the pressure always decreasing when the temperature is cold, or is it increasing? What's happening, like? Mhm. Happening. So what do we figure out with these things?
The pressure's at one. Okay, they're moving. They're kind of moving. They're
What's
kind of
happening
moving.
with the pressure when that
It's a
happens?
decrease the volume.
Yeah, so I decrease the volume.
Why is there two increases?
No volume.
Because this is its home run,
Shit, I'm gonna
and
reset
this
it.
is its home run.
No volume.
So this is your example run. So
Now
this
what?
is showing you that
Increase the temperature, decrease the
when these
volume.
two increases
there was-
Pressure.
There was a lot of.
Sometimes the
There
pressure
was, I think,
increases, and sometimes the pressure decreases.
So when my volume increases.
volleyball, really,
This is the next
Josiah was
relation
there,
is figuring out what
Harris was
happens.
Oh wait, the law banquet?
Still increasing,
No.
but the
Yeah.
temperature is decreasing, which means you go from hot
It's
to
a law.
Yeah, I'm just trying to figure out how to read this thing.
Oh, no, you're fine.
Like this part where I was just like,
Okay, let's do this one
Temperature.
together.
How'd you do that?
yeah.
How'd you already increase it to the max?
Expand your container,
Whoa.
so you just increase the volume.
Oh, maybe I just needed to reset.
Add a little bit more particles.
Particles.
When you do that, the light dies. You have to kind of like balance it.
Okay.
Because
Slowly,
it doesn't
Okay.
die.
slowly.
Okay, just add your particles. Okay, that's enough. Okay,
Turn
look
light.
what's happening right
You're trying to
now.
look on.
See it right now? It's still kind of going up. So that's telling me that the temperature is still up.
Maxing it out.
These red ones like to move a lot faster than the.
Come back, come back.
Watch what's happening.
Okay, this is hard. This is hard.
This thing's
Oh,
high.
okay, this is hard. This is
But
hard.
what's happening
What are you
with the
doing?
gas particles?
Because he's trying to max out the particles, but the light
So the
keeps flying off.
collision is
No,
decreasing.
return. No, Shelby.
But what you see-
It's not coming back.
I maxed out the particles.
Yeah,
No.
we get
Max
that
out the
heat.
You
particles
also have
and
to
max
add
out
heat.
the
You're at 14 Kelvin.
So what does this tell you about your
Yeah, it'll
pressure?
pop off in a minute.
Okay, yeah. I'm just gonna. I'm gonna start writing my conclusion now because I'm not getting any more data from
A
this.
little bit more, so
These blew
what
up very easily.
I think it's safe to say that I know what happened.
It's still increasing, still the same size,
Oh, I
it's
thought you just
contained,
had like one
but your
red
temperature has
No.
decreased.
Oh.
Less pressure.
Lid explodes.
The pressure constantly increases.
Just look at your gas part, your gas particles is
Oh,
telling you
there we
what's
go.
happening. So it's freezing, right? So there's no movement, no collision, so your pressure is zero.
That's an increase.
See,
And
when you're in a
can I blow the
container,
top off with just 200 total molecules?
Explanation.
My goal.
so, okay, is there pepperoni?
Yes.
Okay, so when you have a container, the whole purpose of pressure, you know, you have a pressure lock in the bag. So even though we couldn't physically see it, we knew that the bag was expanded with the vinegar and the baking soda, because the particles was bouncing
Oh,
up
it's gonna
against
explode. It
the gas
exploded.
particles, does that make sense? This is telling me the reaction is done, it's no more, like, when our bag went cold, what happened to the fizzing? Did you see any more?
It slowed down a lot.
It slowed down a lot, it stopped, the reaction was no more. Is that? So, what does this tell you about, so, there is a relationship between volume and temperature, because it will affect our pressure, right?
Yes.
So, what's happening, so what would you say what's happening with the pressure when the volume is increased and the temperature is decreased?
Pressure goes all the way down to zero.
Decreases and decreases. So
The gas particles are no more activity, right?
volume
There's no more
decreases,
collision, the
temperature.
gas particles are not heated up, so they're not moving
Oh,
around.
this light's making
So
me
they stop.
I like it. I like it.
What?
So this is just showing that Charles law, right? Charles law says that volume and temperature, you know, if something happens to the other one,
66
that
Kelvin.
they have a relationship with each other. And this
I
shows
don't mind.
it,
Why
and it
did
will
mine-
affect everything else, like the
Because you're
pressure
bad.
and everything. Is that, are we okay with
So this bottom right here is temperature.
Can I make one
that?
heavy
So
part?
this is volume, this is the size of your
I
food.
want it to be.
Temperature is like,
Mention
You know what a big
But I'm just confused by like, where's the bottom of this like? where am I-
so this right here, you're gonna put down what you just started with the pressure. So like when they did volume and temperature increases, they said, they saw that, I'm sorry. They saw that pressure increase, but it also decreased.
So the bottom right here is pressure.
So you're gonna detail what happened to pressure.
I think that it just takes
So
it
what,
off.
what we saw is that pressure don't increase. You know what I mean? It slows down, it stops, it decreases completely. Okay.
So this bottom row, this whole thing's pressure.
Yes, this is just saying what's happening with volume and temperature.
Yeah.
Like, when I increase the volume, but when I turn down the temperature, decrease it, what's happening with my pressure? So you're gonna write right here what happened to your pressure, what you just observed. And then, in your own explanation, you're gonna try to tell me why. That's why I'm trying to get to the why part, does that make sense? Okay, good. How are we doing,
Take a
children?
while and let everything blow off.
Okay.
We're about to hit, 20,000 degrees.
So this
Now it's small.
So you see how it's
Decrease, decrease.
Okay, so decrease
Gauge,
in
bro, I'm gonna be able to blow the top off of 2 more at once.
increase is greater than the temperature.
I maxed out the temperature gauge.
Because the volume
I have to do it by hand.
greater than the temperature.
Ooh, I need a collision counter.
What's happening with your gas bar?
A collision counter? That
Yes, you can add the
And what's happening with the pressure? It
person.
stops.
Oh no, she got locked out.
RIP.
The volume increases slightly, and the temperature increases slightly. What happens when the temperature changes?
I was like, am I just dumb?
No, that happens all the time.
Pressure's gonna just.
I was just, you have to stand there awkwardly for a second.
Do they know that?
No, you'd have to stand there awkwardly for a minute like every.
Decreases when the temperature changes.
So volume increases, temperature increases.
The pressure goes down a lot.
When it's greater than the temperature, the pressure will decrease. Does that make sense? Because this right here, the reason that over time, even though your temperature is still increasing.
No, come back.
It's, eventually it's gonna cool off.
Yeah, I maxed out the temperature. I put 2 molecules in there, like a light and a
So,
heavy.
what happened when it got
You know what it
heated?
is, man.
I mean, like, it's not fizzing out, it just looks like vinegar. So,
Alright, we're putting 500 each. No, give you 750.
because if my volume increases,
750 each.
even though it's my temperature's gonna increase.
1,500.
I don't know what it can see now. So you're in the camera.
Collision counter,
What?
counter,
It's
counter.
definitely not, but you need to be able to.
I was like, standing there like,
Oh my god.
that's great.
That's a lot of water.
Oh, it's just dead air, so.
Actually, can we?
Oh,
Yeah.
I saw that the volume was doing,
Yeah.
but the temperature decreased. and
Look at her
my
go.
was just-
There you go.
How would you explain that?
Sorry, say that again.
Like, why the reaction was not good?
Just whole VODs, just on YouTube, for the like classroom episodes. It's great.
We can just call it the classroom, you know, like the office, but
The class.
it's better.
Usually Mr. Jones does like a whole intro and stuff. It's so
Because
funny.
like it's saying like when you
Because
increase
you're
the
like
volume
teaching
and
kids and
you
it's like,
decrease the temperature, what happens to the pressure?
The more I put pressure in, the more the gas
Okay, I
is
get it.
hitting
Thank
the
you.
boiling. It's fan.
That's what I think.
Now, what happens if I slow it
That's
down?
what I'm-
doesn't require fancy equipment, just
There's
tripod
no
and
more
phone.
gas particles in there to do anything.
Temperature.
Is that okay?
This one. Thank you.
Oh no.
For this, you ready?
I don't think ice could get this stuff to like 20 Kelvin.
Huh?
Just saying.
Probably not.
A bucket of ice
Probably
or a
not.
bucket of fire gets it to 30,000 degrees.
So the only thing I'll say right here
The pressure kind of remains constant.
is this part.
Alright, I'll
I
slow
don't know
it
what's
down a
going
lot.
So when you
Um,
guys fill those, yeah, just fill those in.
Cage
That's
promise.
being able to explain
Slow down to
why.
0
Why? What's the
with
reason why?
750 each. I mean, do it to 0 ATM and then count the collisions. Do a little science.
So for the first question, when you just add the thing with it, like the pressure doesn't change at all, they just do the normal. So what are you learning? Yeah.
Wow.
Explanation of this one. Yeah.
Particles are fun. Volume is constant, temperature increases. Constant.
Yeah.
I've already done
And
it.
we'll turn it around on February, and we'll explain why it's an ideal gas ball.
Okay.
Oh no. Oh, it exploded.
Conclusion questions.
The lid exploded.
They're spreading out to maintain to fill the container. Yeah.
Yo, Cage, bro, look how compact I got these. I slowed them down
Quick question.
and then squished the
So
volume.
for number 2, it says when making volume, pressure, or temperature constant, what happened to the gas particles?
So here's your constant, right here.
Oh,
So, yeah,
okay.
you're
So,
fine.
so we just press these and then.
See what happens to your gas particles.
Okay.
So your volume is constant right now. So what's happening with your temperature and your pressure? What's happening with the gas particles? Like, are they bouncing off the walls? Are they
So then,
frozen?
do I make them all constant at once, or? do I
You're
go
just
through all
making them
three?
individually constant.
Okay.
I'm sorry if I didn't explain that properly.
So then, should I increase
Yeah.
the temperature when the volume's constant?
You can make it increase or decrease.
Oh, okay.
So these are just conclusion questions, like when the volume is constant and the temperature is increasing, what's happening?
Okay.
Okay, when the volume is still constant and the temperature decreases, what's happening? What's happening with the pressure?
Which one? We learned about.
Can you help me with something? Is it, are you asking for proportionate direction for the second question? Does it ask when it goes pressure, temperature constant, what happens to the gas particles? And then it asks what happens, like on the Boyle's law and Charles' law. Yes, it's gonna be like, so if pressure and temperature is constant, volume, or if volume and pressure are constant, you're just changing temperature, things like that. So if any combination of these are constant, what happens is the only thing you're gonna change is as your temperature changes. It's just all so just, you know, because it's liquid volume. Okay, does that make sense? Okay, yeah. Thank you. Double asked. So if you do volume, yeah. Was it that? If volume is constant, here, I'll just put it on here. Volume is constant. It's dropping. Yeah, there you go. Okay, well then it goes back up.
This is your constant, so
Yeah.
like, when I meant, if volume is constant, what's happening to your pressure? Like what's happening, if one is constant.
Okay,
And then that should have been another question.
it drops and then it goes
Oh,
up.
hey y'all, on conclusion question 2, it says when you're making the volume, pressure, or temperature constant, what happens to gas particles? So just describe if you have volume and pressure constant, you're changing temperature, or if you have pressure and temperature constant, or volume temperature constant, like just any combination of those ones that are constant, describe what's happening. The second part says if you were to change the size of the container, that's just asking the volume again, so scratch that part out, you're fine.
That meant to be another question on
slow
its
down.
own.
Okay, so yeah, just focus on basically describing these laws to us, okay?
Hey, check it.
Okay, so
I
pressure
got max
doesn't
particles
change.
without blowing the top off in the smallest volume.
So how are we doing?
Doesn't change, like if volume is constant, the other two don't change.
It don't even look like they're moving anymore.
Did I change volume?
I've got them slowed down a
It
lot.
goes way down.
I
like
max
whatever
out the
the
volume
is,
and then I
it
max out the
changes the
particles
pressure.
and then I slow them
More
all the way
quickly
down.
than it changes
And
the
then
pressure. So like
I
if
was
I did
trying to
like
see if I would
temperature,
close
yeah.
the sugar
And then if I
close the top
expanded
right
the
there.
volume,
So why is it
it
not?
goes like way down there.
Because it has almost zero
And if I
atmosphere.
There's no pressure.
So like watch this, it goes down.
My head is probably just
I mean, like,
at the
that's
bottom
still
of
kind of
the
hot,
entire
but
video.
like, that's not that much for having
Yeah, but you have to
so many particles in there.
And if it isn't, I shall be surprised. I'm gonna go back and look at this video and it's just gonna be
Good observation right there.
We're not even in it, that's the thing.
Oh, that's good.
Yeah, it's like, even right now, we're not in it.
It might be because it's zoomed in, like, to
They
1.5.
said to like
Yeah.
change between the.
That's a good thing. It means I'm not in the
I
whole
mean, I was
thing.
standing right there and I was
So
like,
like change
I
volume.
know, hey, you're on camera, and I was like, oh, hey. Sorry.
I love doing that
Being
because,
completely zoned out.
I mean, like, it's facing the board most of the time, so like, just
But
standing
we
there,
have
like,
to get
can-
videos of us talking to y'all anyways.
Yeah.
So that's why I was like, let's just go show which is included. Oh, yeah, there is right there, way down there.
How we doing, Shelby?
I'm doing pretty good. I have to answer the conclusion questions now. And not get distracted by all
That second part of it meant to be its own question,
I wish we
but
didn't
it's
have
still
to
open.
hold the temperature thing.
question.
I know.
We could just set it at a certain amount of Kelvin.
Oh, it's whole bunch again. But simulations are nice.
Which is
Simulations are nice, though.
Are you learning anything?
Yes. I very much
No
enjoy
way.
this.
I got it to 273 Kelvin.
Can I? He's just like,
It's gonna break it, like the road snap race last year.
No, I'm not. It's not possible.
Brakes? Oh wait, brakes now.
He literally, he
cooler.
basically emailed,
My bad.
he basically emailed every lawyer and all.
I'm Alabama in Jefferson and Shelby County.
why did he email every
So
lawyer?
could we just
How
like
much
talk
money
about
did I
that
raise?
as a whole
Like,
instead of saying
I think it was
To get
over
money.
$4,000.
Oh, asking for money?
Just me.
That makes sense. That sounds like something he would do.
It worked though. No, law. Like we just had to. Like the thing is that
edited
a lot of the lawyers they're smart about their taxes and they do them themselves, so they know that if you make donations to the school, you can get you can write it off and like act like it's tax.
No.
So
The right
basically they
letter
got-
shape.
Basically, you pay less taxes.
Or not really. The money goes more directly to where you want it to go, if that makes sense. So the money, they probably tax me and
Instead of just
some
going
money
to-
to like maybe highways and schools. But if I donate $1,000 to a school, I can get that off my taxes because like it's what the taxes are already gonna go to, if that makes sense.
But it's more
But it's more
specific.
specific, exactly.
Whichever
So.
two are constant, find the one that's relationship with the other.
Okay, perfect, yeah, that makes sense, thank you. Wait, so number 2 is supposed to be 2 different questions?
Alright, we gotta hold this constant temperature. Nice.
So the, if you were to yeah, for sure. Okay. Don't answer at all.
Where do volume come
Because the size of the container is.
Okay. Just time check, 7 minutes.
Would be.
Hey, so I'm just gonna look, is everyone almost done with this simulation? Is it okay if we just, we're gonna bring y'all back into the front of the board and we're just gonna talk about it
Where
together?
did my thing go?
If you're still filling out this,
Got him.
still kind of fill out the,
Check my mouse.
Do we need to put the camera?
Oh, yeah, probably.
okay, since we went over the first row, what did we find out with our second row? When volume increases and temperature is decreasing, what did we find out about our pressure?
The pressure kind of stays the same because they kind of cancel each other out.
Okay,
Or just overall, when you decrease the temperature, the speed of the molecules decreases a lot, and if you get it down to 0, there's no pressure because the molecules aren't moving.
And if you open the lids, the pressure decreases. I mean, the
Because
pressure
all
and the,
that
and
is-
the temperature.
Hey, in terms of temperature, what's our little catchphrase for the motion?
Heat 'em up, speed 'em up.
Heat them up, speed them up, cool them down, slow them down, okay? And then what causes pressure? Collisions, so if you open up the top and let the molecules go out, what happens to collisions? So what happens to pressure? It's less. In a hot air balloon, when they're wanting to come down, they have a little flap at the top, they can open up the flap and let air out, okay, so then the balloon volume goes down, the pressure goes down, and it sinks.
So does anyone wanna give me their explanation, what they put down? For when volume increases and your temperature decreases? Hudson's group.
Volunteered.
When the volume decreases and the temperature increases, it first, when you decrease the volume, the pressure increases, but then when you, take up the, temperature, it really starts to increase the pressure, and it almost always explodes the top of the, thing,
Okay,
because it's so much pressure.
thank you. So what happened when you decreased your volume and you increased your temperature? What happened to your, yes?
Pressure went, up.
Okay. What was your explanation for that? Being able to explain it?
Decreases and increases. There's very little space for the molecules to move around, and temperature speeds up the molecules. So with the speed and like the constant hitting of the container walls, the pressure increases, and like Hudson said, it almost always explodes the container.
Because the container, the volume of the container was smaller, so the gas particles didn't really have any move to go, so they were colliding more, so made your pressure go up. Good job. So what happened when your volume was constant? This group right here, what happened when you had your volume, your constant? And your temperature was increasing? What happened to your pressure?
Yeah, pressure would also increase because the more particles that we were doing, they'd be hitting each other faster and increase the pressure. You have to level it off.
So we're just gonna go straight to the conclusion questions. So number one, what are the gas particles doing when they are first added to the container? When you're first doing the simulation, you're adding those gas particles, what's happening?
They're spreading out to fill the size of the container.
Okay,
They're diffusing.
okay. Number two, so what happened when you made your volume constant? Well, never mind. Your pressure constant, what happened? Did it affect the temperature of it, anything?
Okay, so if you have your volume and your pressure constant, but you're changing your temperature, what happens?
The pressure's gonna start increasing.
Okay. So your pressure is constant.
Oh. Temperature increases.
Temperature's increasing. Okay, so what is happening when you are heating your container up? If you're just heating it up, what's happening? You just said it. That's not gonna go.
Well, the temperature increases, so it speeds up the molecules.
Speeds up your molecules, and that'll make your pressure increase if you're just heating it up. If you're cooling it down, what's that gonna do to it?
Slows them down.
Slows them down. Yep. Okay. And does the size of your container affect your particles? Is your volume gonna affect it? Yeah. Okay, so if I increase my volume, then what's gonna happen?
Less collisions, and will be slower because there's more space for them to like miss each other.
Yeah.
And then if they're in a smaller, tighter one, then they're gonna hit each other more because there's less space for them to miss each other.
So your pressure is gonna go up if your volume increases or decreases.
Volume decreases, the pressure will go up.
All right, and which law is that using?
Boils.
Oils?
Oils. Okay. So are they inversely or directly proportional? Inversely proportional. So if one goes up, the other goes down. Okay. Does that make sense, y'all? All right. Awesome.
Like we did yesterday, will y'all do an exit slip for us? 3 things y'all liked and 1 thing y'all may still not be understanding.
y'all. I think this is gonna be
This
our
is our
last
last time
time.
seeing y'all.
No.
Yeah. Yeah.
So if y'all wanna do, actually, let's do like three things that you liked about, or three things you like overall. So
Yeah.
we've been here a couple times, like we watched y'all, we taught a couple times. So things that we can do to improve overall, because we're still learning, clearly. And three things that you thought we did okay y'all? Thank
And
y'all.
y'all really have done a really good class, and thank y'all for just being with us, and riding with us.
Yeah.
Let us figure it out. Yeah.
No, well, I mean, didn't they answer? Well, bring the worksheet on Monday, we'll
Can
get
you
it
tear
in
off some
and
of
get
that
class
for Jacob?
paperwork.
What? You tear off the bottom half of that sheet.
You wanna give me
Give me your I gave all of you guys a piece of paper. I want every single one of you. I gave all
Not me. Alright, Paige, my part is selfish.
we're so strapped.
Yeah, but
And I'm gonna take a picture of you.
Brendan's sheet, you sure you want his handwriting? Yes. Oh, this one.
In the back, 'cause I know.
Yes. Oh, and mine too? Which one?
Just the Phet Simulations. I think you have great handwriting. Yeah.
Lies, you lies.
Great.
Lies in the night.
Okay.
Hey, say whatever you want.
We're not gonna be doing well.
Three things.
They have not been here all day, just.
Okay, well, I guess we should probably end the video. Would you like to say anything to the people?
Hey, like and subscribe.
Yes, like and subscribe. I don't know. At this point, get Mr. Hop to 100 subs. Goodbye, everyone.